Okay, let's start something from information theory. And very basic topic on information theory is known as entropy, or which is also known as self-information. Basically, the way Shannon describes this self-information is this: event that has a very low probability, it has more information. All right, that's what this definition is saying. So this is entropy, which is known as self-information. And the event that has more probability, less probability of happening, which means it contains more information. An event that has very high probability of occurrence, it has low information. Let me give you an example of this. The basic example of this might be something like it will be sunny tomorrow. uh, okay, the probability of this being sunny tomorrow is very high, which means you did not gain any information. According to Shannon, you did not gain any information. But when I say that it's gonna snow tomorrow in Karachi, there is the probability of this happening is very low. But the information this sentence contains is very high. The probability of this happening is very low, but the information is very high. This is how Shannon describes Shannon entropy. And we're going to learn how to calculate this Shannon entropy. Based on the Shannon entropy, we're going to decide we can make efficient codes. Follow-up video is going to be on something called Huffman coding. We can decide we can send less bit to convey the same information based on this Shannon entropy. This is the starting point where we can generate efficient codes, source code actually, where we can depict the same information using less number of bits. So in this example, what we're going to do, we have a sentence like this: a mathematical theory of communication. And I'm going to describe each of these components, and we're going to calculate how many bits can be used to represent this entire sentence. And based on that, we can design or devise efficient source codes. So let's break this video because let's just call this an introduction video. Okay, so I'm gonna stop this video now, and then I'm gonna make them in probably in 2 parts or something like that. Or let's just do it. So the way I'm gonna do it, let's say I have a sentence like this: mathematical theory of communication. So the way I'm gonna do it, I'm gonna count number of letters that are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So the number of, so we're going to do frequency analysis first. I think I forgot. So the total number of letters, so total number of alphabets that we just counted, alphabets, is equals to, I think, 33. So now what we're going to do, so what this saying is this: we need to find the probability of each of these alphabets in this sentence, and find the probability of that, and take log base 2 of that probability, and then add them up. At the end, we will get the total number of bits which we can use to represent this entire sentence. Okay, so I found total alphabets to be 33. Okay, so let me write it down correctly. And then what I'm gonna do, I'm gonna do how many times each letter has occurred. So let's take A. So we are calculating the frequency of that. So A is 1, 2, 3, 4, 5. A has occurred 5 times. And how many total letters are there? Is 33. So based on that, we're gonna compute the probability of that. So this is going to be 5 times. A has occurred 5 times, divided by the total number of letters. So that would give me 5 divided by 33 would give me 0.15. So the probability of A occurring is 0.15. We're going to take the second letter now, which is M. We're going to ignore the spaces. We're going to ignore the capital letters. We're just taking the letters as is. So M, 1, 2, 3, 4. So A has occurred 4 times. Divide by the total number of letters. So that is going to be, so let's bring out our calculator. So this is going to be 4 divided by 33. So that would be 0.12. The probability is 0.12. Okay, we already checked out A. M is gone. Let's pick up 3. So I have 1, 2, 3, 4. So T has occurred 4 times. So 4 over 33 would give me 0.12 because it's the same number. Let's pick up H. H has occurred how many times? 1, 2, and that's it. Only 2 times. So H is 2 over 33. So the probability of that, 2 divided by 33, would give me 0.06. That's the probability of H. Now let's look at E. E has occurred how many times? 1, 2, only 2 times. 2, sorry. E has occurred 2 times. So 2 over 33, that would be the same as 0.06. Let's pick up E is done, M is done, A is done, T is done. Let's pick up I. I has occurred 1, 2, 3 times. So I is 3 over 33. So 3 divided by 33, that is 0.09, 0.09. And let's do it here. So we have I. How about C? C has occurred 1, 2 times. So C is equals to 2 divided by 33. So that would give me 0.06, 0.06. All right, so far so good. What about A? We already checked out A. What about L? L has occurred 1 times. So L is equals to 1 over 33. So let's pick our calculator. 1 divided by 33. That would give me 0.03, 0.03. Okay, what about, so we're done with T, we're done with H, we're done with E. What about O? O has occurred 1, 2 times, 3 times actually. 1, 2, 3. So O is 3 times 33. So 3 we already calculated to be 0.09. The probability of that is 0.09. So 0.09. What about R? R has occurred 1 times. So R is 1 over 33. So this would be 0.03. All right. Let's say what else is left. What about Y? Y has occurred only 1 times. So Y is 1 over 33. So that would be 0.03. All right. What else is there? O we already taken care of. F has occurred 1 times. So F is 1 over 33, 0.03. All right. Let's say anything else is remaining. C, we're done with C, we're done with O. What about U? Okay, U is also there. U has occurred only 1 time. So this is going to be 1 over 33 is equals to 0.03. What about N? This is H actually. So N has occurred how many times? 2 times. 1, 2. So 2 over 33. So that would give me 2 over 33 would give me 0.06. All right. So far so good. So we have 2, we have I, we have C. What about O? So I think we're done. So these are the number of probabilities. These are the alphabets which have occurred in this sentence this many times, and these are the probabilities of that. Now the idea is this. I can either write it with negative. Why we have a negative sign here? Because of 1 over log p of x. When we divide this, I will get negative sign. Here we're just simply multiplying it. So what we're going to do, we're going to plug in each of the number of probabilities. Like let's say A, we're going to plug in that. And then we're going to take a log base 2 of that probability and then we're going to multiply them together, and then I'm going to continuously add all of those alphabets, and after that I would get the number of bits uh, which are needed for me to transform or send this data to my receiver.